So, this week's plan is to do a little bit of sklearn, which you'll have to use for your assignment now. And then we are going to start hidden Markov model, okay, which is another very important machine learning technique, mainly for sequence leveling. So last week, the main points that were covered are a bit of prologue, where prologue is actually based on recursion and make and break. So the main data structure there is list. The list is often broken up into two parts: the head of the list, which is an element, and tail of the list. Tail is another list. Okay, so and also it makes a heavy use of recursion. For example, to compute the length of a list, we just add 1 to the length of the tail of the list. So you can see compute length is calling itself with tail and the length of the tail. And the boundary condition is that the termination condition is that for empty list, compute length returns 0. So the two things to note here are recursion and breaking the list into two parts, head and tail. The syntax of prologue is a simple one. You have head, then the neck operator, and then the body. The neck operator is read as if. So likes John X, if likes X cricket. So John is fond of anybody who likes cricket. Okay, so this is the syntax. Then we started support vector machine. And in support vector machine, again, we set up a linear classifier, a hyperplane to separate the two classes. But there is an addition. So support vector machine is like perceptron setting up a hyperplane to separate the two classes of the points. But there is an additional requirement that the hyperplane should be set up such that it has maximum margin. So the distance from the support vector of the positive class plus the distance from the support vector of the negative class, that has to be maximum. So there are theoretical proofs that such a hyperplane with maximum margin generalizes the best. Yeah. And empirically also this has been observed. Support vector machines were extremely successful in what is called document classification. Finding out if a document is belonging to a particular class or not. Okay, so that is for example, is it a document on sports or economics? That kind of decision, support vector machines were very good at. So the maximum margin is maximized by minimizing half WTW, where W is the coefficients for the hyperplane, subject to the constraints which are shown here. Then there is a kernel trick for support vector machine, because support vector machines cannot separate nonlinearly separable classes. So what kernel does is that it moves the points, okay, or it increases the dimensionality of the problem and places the points appropriately so that they can be classified. For example, we know that on the plane, XOR cannot be classified, right, by a hyperplane, because the two classes are diagonally opposite. The positive classes are diagonally opposite to the negative classes. So by kernel trick, what you do is that you raise the positive points above the plane on which the negative points are. Okay, so the negative points are here, positive points are here. That happens to the kernel trick. And now you set up a hyperplane in between. So that achieves the separation. So this is the kernel trick. And those were the main points covered in the last week. Now, this week in the lab, you will have to create a SVM classifier for a data for a set of data points, which will be specified to you in the lab. And for that, you will have to use the sklearn package. sklearn package, I think some of you have already started learning from the lab. So this is an example where there is a data from the UCI machine learning repository. The number of instances is 748. This is not your assignment. Okay, it's just for illustration. The number of attributes is 4. And there is a decision to be made whether a person with these 4 attributes donated blood in March 2007 or not. Okay, it's a binary decision. The attributes are recency, frequency, monetary attribute, and time. So sklearn is the package you'll have to use. You don't have to implement support vector machine ab initio. So in this, we'll have to be careful about various measures. I'll come to that. So you have to import what is called pandas. So pandas is a data incorporator. Okay, so it is a it produces what is called data frame. So there would be positive points and negative points. And then you will have train, test, and split, train and test split. Okay, validation set also. And then you will have to import the standard scalar. That is a very standard technique in machine learning. What happens is that so that no attribute dominates other attributes. Okay, some attributes possibly have a different scale. Okay, so if you take, for example, age of a person, the age of a person is between, let's say, for the purpose of loan. So that's between maybe 20 and 60 possibly. So this is a set of integers. But the income of the person, let's say, is in lakhs per annum. Okay, so that would be a much larger integer. So this integer is very large compared to the age integer. Of course, you can apply decimal points and so on, divide by 100,000 or whatever. But this attribute as such will dominate other attributes because of the sheer size of the values. So typically what is done is that you would use the standard scalar to subtract the mean and divide by the standard deviation. So some kind of normalization you do on the attribute values so that these attributes do not have this mutual dominating effect. Okay, so pandas you will have to import for, you have to use pandas for data absorption, standard scalar for normalizing the attributes, and then you will run the support vector machine classifier. The accuracy is reported, or the performance is reported by precision, recall, F-score, accuracy, etc., and it produces a nice report. Okay, so this is the way the package will have to be used. You make sure that you become familiar with how to use this package. Then it also comes inbuilt with kernel tricks. For example, radial basis function is a popular kernel for support vector machines. Okay, so all these are incorporated here. And then you get all kinds of values. So precision, recall, F-score, all of you know are bread and butter for machine learning. So let's do a bit of discussion on this. Suppose this is your concept class. So the black circle is the obtained labeling, and S2, which is this set, is the actual labeling. So these are the people, okay, here, whose labels are actual. Okay, so loan granted or not granted, and so on. So sorry, these are the loan granted people, and outside these are people whose loan is not granted. It is a binary classification. And our classifier has absorbed these points. Okay, now you can see that S1, which is the decision made by the classifier, intersects with S2, the actual concept class, in this region. So there is agreement between labeling of the classifier and the actual labels in this region. This is a region which is missed by the classifier. So this is a false negative region. Okay, this is a region which is falsely labeled as positive by the classifier. So this is false positive. This is false positive. This is false negative. This is true positive. This is true negative. Okay, outside. So precision is intersection of S1 and S2 divided by the size of S1. Recall is intersection of S1 and S2 divided by the size of S2. This is precision and recall. So now, in terms of the what is called the contingency table, so actual are yes and no, obtained are also yes and no. So A plus B is the row total, okay? And C plus D is also the row total. The total number of instances is A plus C plus D. So this is the region where there is agreement between classifier and the actual concept class. So A is true positive, C is false positive, B is false negative, wait a sec, and D is true negative, false. Oh, this is obtained. Okay, so this is the obtained class and this is actual. So therefore C is false positive, fine. Okay, and B is false negative. So then precision and recall, they can be represented in the form of true positive, false negative, true negative. So precision is actual intersection obtained divided by obtained, which is A by A plus C. So true positive by true positive plus false positive. Recall is actual intersection obtained by actual, which is A by A plus B, which is true positive by true positive plus false negative. Okay, so these are very standard metrics which are used in machine learning. And you either have been exposed to this before or please get exposed to this and absorb it completely now. Now, precision and recall have a kind of inverse relationship. If you increase precision, typically recall falls and vice versa. Okay, so intuitively, the reason is that as you try to move the classifier set, okay, the labeled set by the classifier towards the actual set. So this circle begins to enter the region of the other circle. Okay, so this goes on increasing. This intersection region goes on increasing. Okay, however, these false positive, false negative class regions also undergo change. And if you see the formulation of precision and recall, which is true positive by true positive plus false negative, if you increase precision, then recall typically falls and vice versa. This is quite apparent from the behavior of false positive and false negative. Okay, so precision increasing would mean A increases and also the false positive begins to reduce. Okay, but that may mean false negative begins to increase and that would interfere with the performance on the recall. So precision and recall typically have a inverse relationship. So what happens is that you try to come up with another metric which combines precision and recall. So the simplest form of combination is when precision and recall are given equal importance. If they're given equal importance, then beta value is 1. So beta value 1 means F1 score is equal to 2 into PR by P plus R. 2 into PR by P plus R is nothing but the harmonic mean of precision and recall. And what is the property of harmonic mean? The property of harmonic mean is that it gives importance to lower of the two values. Okay, arithmetic mean is biased towards high values. Harmonic mean is biased towards low values. And that indeed should be the case. If both precision and recall are important to me, okay, then I should give importance to the lower of the two values, because the other higher value will automatically rise in that case. Okay, so it is like importance being given to the youngest child of the family. Okay, the eldest child typically gets importance, but suppose I want to give importance to the youngest child of the family, then harmonic mean has that behavior. One may wonder why precision and recall are not averaged. Why don't you take arithmetic mean? If you take arithmetic mean, the arithmetic mean is biased by the higher of the two values. So this will give a wrong picture. Okay, you might increase the recall only, sacrificing precision without being aware. Harmonic mean, on the other hand, gives importance to the lower value. So you are fair to the or you are taking action for improving the lower of the two values so that your performance is balanced. Now beta decides who gets how much importance. Okay, you can check yourself as you increase beta, who gets importance? Is it recall or precision? As beta tends to 0, who gets importance, precision or recall? Okay, so this is called the F beta score, and the precision and recall are combined through this. So precision, recall, F score, all these have to be computed by you for the data set that we will specify in the lab in implementing the support vector machine. Okay, let's proceed now. Let's take up a very important topic, which is the hidden Markov model. Hidden Markov model is important for sequence processing. Okay, labeling the sequence. Where does sequence processing appear? So in computer vision, sequence processing happens in the following way. If you look at the picture here, so you can see a person is lifting a box. So first there is this half bend posture, then bend, then down squat, then sit, then up squat, then half stand, then stand. Okay, so you have a sequence of postures, and at the end, the effect is that the person has lifted the box. So this kind of sequence of postures labeling and detecting is extremely important. Okay, for example, in airport surveillance, so there are CCTVs everywhere, and it is continuously watching the movement of people. If there is any suspicious activity, a red flag will be raised, and the airport security system will be alerted. So suppose there is a sequence of operations which the machine learning model has from its data and previous experience found to be suspicious. Maybe that sequence led to a terroristic activity. Okay, so this kind of data is given to a machine learning model, and each posture is labeled, and final decision is suspicious, non-suspicious. Okay, this is how the data is, or even each posture is asked to be labeled by the machine learning system. So this is one Very important example coming from computer vision. And this labeling is done by human beings. Okay. In language, where the sentences are sequences, labeling of sequence and detecting the property of the sequence is extremely important. So one of the basic tasks is what is called part of speech tagging. Most probably your hidden Markov model based assignment will be on part of speech tagging in a simple form. So I take this sentence to bank, to bank, I bank on the river bank. To bank, I bank on the river bank. So to bank, here bank is a verb. Okay. To bank means to do banking transactions, opening account, withdrawing money, depositing money. This is the banking activity. I bank, this bank is also a verb. This means depend. So to carry out my banking transactions, I depend on the bank. This is a noun on the river bank. Okay. So you see the word bank appears multiple times here with different parts of speech. So to is a preposition. The first bank is a verb. Comma is a punctuation. I is a pronoun. Next bank is a verb. On is a preposition. The is a determiner. Next bank is noun. On is a preposition. The is a determiner. River is a noun. Bank is a noun. So this kind of part of speech is placed on the words so that the next activities, downstream activities can be carried out. Okay. So this is again a very important activity. So we have taken one example from vision, one from the language side. Now we need some preliminaries. Okay. The preliminary is what is called the noisy channel model. The idea comes from automatic speech recognition. In automatic speech recognition, what happens is that you have the spoken utterance signal coming into the channel here, and out comes the words. So for example, if now you had a automatic speech recognition device with you, whatever I'm speaking will go into your device and get converted to text so that you don't have to take any class note. Okay, it will be automatically transcribed and given to you. So this signal which is coming in gets converted into a text. The term noisy channel comes from automatic speech recognition because most of the time a spoken signal into text has its own imperfections. Okay, so so if just listen to me carefully now. I got a plate. What did I say? Can anybody say? I got a plate. You say slowly. मैं देर से उठा. That meaning, right? Any other? I got a plate. मुझे एक plate मिला. Versus I got a plate. Okay. So typically we have ambiguities, and this ambiguity is coming from the ambiguity of word boundary. I got a, then plate, or I got up and then late. Okay, where is the word boundary coming? So that is an ambiguity. Also, we typically hear in noisy environments, and that's why the transcription can be faulty. So the noisy channel means it converts the input to output with imperfection. And because there is imperfection, you have to make use of probability. The other point is that there are pronunciation variations. Okay, so for example, tomato, the pronunciation could be tomato or tomato, depends on the region. And one of the classic examples is the pronunciation of car. So there are regions in USA where the final R is dropped. I got a new car. R is dropped. There are regions where this R is extremely hard and harsh. Did you see my new car? R. Okay. In India, we neither drop raw, the final raw, nor do we make it harsh. Did you see my new car? R. Okay, so there is pronunciation variation, there is a noise in the environment, there is ambiguity of word boundary. That's why you have to necessarily bring in probability. You have no other go. Okay, so we have done a knowledge representation system through predicate calculus. I promise that I have to do another uncertainty management system for knowledge representation, fuzzy logic, that you must be exposed to as a student of AI, and we'll do fuzzy logic. But right now, our vehicle for uncertainty management is probability. So the noisy channel system, it models this kind of transformation of input to output in this way. T star is equal to argmax probability of T given W. So given the W, many T's are possible. Given the speech, spoken utterance, many pieces of text are possible. Choose that text which has the highest probability. So that's why argmax, and T star is the best possible text. Similarly, you can reconstruct the input again through an argmax probability of W given T. Now this noisy channel framework is very, very universal. Okay, it can, for example, be used for this posture labeling that I showed. So you have a sequence of postures coming in. These are labels on each of the postures. You can have a wrongly spelled word coming in. Okay, wrongly spelled word. Umbrella, for example, AMBRELA. And out comes the correctly spelled word. You have a sequence of words coming in, and their parts of speech, the grammatical categories, are coming out. So these are very, very universal and powerful model. You make sure that as a student of AI, once again, you understand a noisy channel model, this argmax computation, and use it for your problems. The modern deep learning systems have an implicit way of modeling this probability of output given the input. The statistical machine learning system before, which preceded deep learning systems, it explicitly modeled this probability of output given the input. Okay, so hidden Markov model is a classical statistical machine learning system, which I'm going to use for sequence labeling. Now, the next important mathematical instrument for us is the Bayes theorem. So probability of B given A is probability of B into probability of A given B divided by probability of A. Probability of B given A is called the posterior probability. Probability of B is prior probability. Probability of A given B is likelihood. So in your data analysis and interpretation course, you have been using Bayes theorem very, very extensively. So in case of argmax computation, one nice thing that happens is that you apply Bayes theorem and you don't have to worry about the denominator. So T star equal to argmax T, probability of T given W, which is equal to probability of T into probability of W given T divided by PW. But since the argmax is over T, okay, PW comes only as a scaling factor. it does not affect the ranking. So you can drop PW and simply have probability of T into PW given T. So this becomes the joint probability of T and W. So if you apply Bayes theorem, then you are actually computing the joint probability. This is also called the generative modeling. Okay, generative modeling. And opposed to that is called the discriminative modeling. So if you don't apply Bayes theorem and work only with probability of T given W, then we are doing discriminative modeling. If we use Bayes theorem and work with probability of T comma W, then we are making use of generative modeling. Why it is called discriminative modeling or generative modeling? What is the significance of discriminative, generative? We will discuss as we move forward. So in case of part of speech tagging, we'll again have T star equal to probability of T into probability of W given T. Okay. So we'll come to these formulations, but let's go to hidden Markov model with a motivating example, which is extremely common. All textbooks and the basic paper on hidden Markov model. The basic paper on hidden Markov model is due to somebody called Rabiner, R-A-B-I-N-E-R, from Jerusalem University. This is a classic paper, one of the most cited. And Rabiner also uses this example for hidden Markov model presentation. So here is the situation. You have three urns or three containers, where the first container has 30 red balls, 50 green balls, and 20 blue balls. The second one has 10 red balls, 40 green balls, 50 blue balls. The third container has 60, 10, and 30. So now the probability of transition from in going from one urn to another is also given. If I have picked up a ball from U1, what is the probability that I'll pick up the next ball also from U1? It is 0.1. Probability of picking from U2, 0.4, from U3, 0.5. Similarly for U2 and U3. Notice that since after U1, you have to remain in one of the containers, U1, U2, and U3, the row sum has to be equal to 1. Okay, so probability of U1 given U1 plus probability of U2 given U1 plus probability of U3 given U1 must be equal to 1. Column probabilities need not sum to 1. Okay, that it happens to be so in this particular case, but the column probabilities did not sum to 1. Okay, let's not have that misconception. So probability of U1 given U1 plus probability of U1 given U2 plus probability of U1 given U3 need not be equal to 1. Okay. So because each cell is defined as the probability of next urn given the current urn. Okay. Also is given what is called the emission probability. The probability of picking up a red ball from U1 is 0.3 because there are 30 red balls out of 100. Green ball 0.5, blue ball 0.2, and so on. Again, the row sum should be equal to 1. It so happens that the column sum is equal to also 1. This need not be. Okay, probability of R given U1 plus probability of R given U2 plus probability of R given U3 need not be equal to 1. Okay, so now we make this observation. The balls are picked up with replacement and the colors are told to us. So R, R, G, G, B, R, G, R. Now we are asking, what is the most likely container sequence from which these observations have come. Okay. So the observation given to us is the sequence of colors. We have to find out the most likely sequence of arms from which the balls have been picked, and this sequence is produced. Okay, so this is the formulation. Now, what is the practical utility? The practical utility is the following. Let's say I am given a sequence of postures. Okay, and I want to label them as half bend, bend, down squat, etc., etc. You can see that up squat and down squat can be confused. They look very similar. Okay, then half stand and half bend also look very similar. However, up squat, if I know the previous posture, then it becomes much more definite. Similarly, half stand, half bend, and so on. Okay, so given the previous posture, the current posture becomes more definite, or given the current posture, the next posture becomes more definite, making use of that information. So the task is to have these observations and give the labels of half bend, bend, down squat, sit, etc. Or it could be that I'm given a sequence of words. I was very happy that India won the Champions Trophy. Okay, so you have this sequence of words. So India winning the Champions Cup. I think it made all of you happy, right? Yesterday. So you have to sequence this with grammar levels, the part of speech levels. For what? Okay, to understand the sentiment, for example, in the sentence later. So I give the word sequence, okay, and you have to produce the part of speech sequence. I look upon the words as observation sequence, and the part of speech as the hidden variables. I look upon the posture pictures as the observation, and the posture levels as hidden variables. Okay, so this particular problem, which is shown to us, is a representative problem for many practical real life examples. So how do we get the probability of the hidden variables given the observation? That is the question. Okay, so let's see how to go about it. First of all, we create, making use of the emission probability table and the transition probability table. Was hidden Markov model covered anywhere in any course before? Hidden Markov model? Any course covered it before? No? Okay. So U1 comes back to U1 with probability 0.1. This I get to know from the transition probability table. U1 goes to U2 with a probability of 0.4. U1 goes to U3 with a probability of 0.5, all from the transition probability table. Okay, so from the transition probability table, I can construct this automaton. Okay, the number of states being equal to number of arcs, and also give the arc weightages in terms of probabilities. Another thing we do is that from every state, I bring out this kind of arcs with probability values on them. So probability of picking up a red ball R is 0.3, green ball is 0.5, blue ball is 0.2, and so on. Okay, so this becomes a representation for my transition probability table, and the emission probability table. So there are three classic problems with respect to hidden Markov model. These are: given the observation sequence, find the possible state sequence, and the algorithm which is used is called Viterbi algorithm, very famous algorithm. Given the observation sequence, find its probability. This is the forward-backward algorithm. And given the observation sequence, find the hidden Markov model parameters. That means get the transition probabilities and the emission probabilities. So this is called the Baum-Welch algorithm. So all these algorithms are very famous: Viterbi, forward, backward, and Baum-Welch. We'll cover these algorithms in the class. Okay, so let me stop today and just remind you that this week's lab will be on support vector machine. The data set will be specified. You will have to make use of sklearn. The slides will be made available today that to facilitate your understanding.